That's about it. Well, I got. Why don't you just, well, this is a great thing about.
So, he's, for many that have listened to astronomy talks elsewhere, Walt is a well-known name and individual, and we're really fortunate to have him again with us this year. Walt Windish became interested in astronomy when he first saw the Pleiades star cluster in the system. He bought his first telescope just in time to watch Halley's comet approach the inner solar system and has been keeping an eye on the sky ever since. He has been giving talks on astronomy at the JWST State Park Observatory and other locations for 30 years and belongs to the United Astronomy Club of New Jersey, North Jersey Astronomy Group, and Rockland Astronomy. We're very much looking forward to this presentation, which is very up to date. I think he'll touch upon the fact that some of the things that he'll share today are findings that have been previously published and made more public. So without further ado, Walt Windish on the James Webb Telescope and
I've been giving talks at basically JWST for many years. And one thing I started when the James Webb Space Telescope was launched, I decided I would give yearly updates. So this is my third yearly update. What I try to do is look back on the year
and look at the most recent discoveries or most recent images and mix in a couple older ones as well. And I'll start off by giving you a little bit background on the James Webb, and then we'll take a look at some of the science that has come out of it. And, you know, every time we send a more advanced instrument, either on Earth or up in the sky, we find data that brings certain theories and ideas into question. And I love seeing scientists scratch their head over data and try to figure out and go back to the drawing board to figure out how to explain that, because it doesn't quite match what they expected or their models. So the James Webb Space Telescope, I'm going to just call it the Webb Scope or the Webb, was launched on Christmas Day 2021 at a little after 7 a.m. It cost us $10 billion. And I say us because if you pay taxes, you got a piece of that. And that's also why everything's public domain. When you go to NASA sites, you give people credit for it, but you own the stuff because you paid for it already. It's a joint project between NASA, European Space Agency, and the Canadian Space Agency. The first 5 images were released on July 12th, so 7 months later. And that's because the James Webb had to go a lot further than the Hubble to get into position. And then it had to unfold itself and deploy itself, and there were over 200 single point of failures. So it was amazing that it unfolded without a hitch, and that's really an engineering feat for sure. The JWST continues to break its own records regarding distant galaxies, and that was one of the things that it was put up there. I would say some of the main objectives is to better study galaxy formations and distant by looking at farther and farther towards the beginning of the Big Bang. Also to look at the expansion rate of the universe. That's still, how fast is the universe expanding? And to find exoplanets. Those are some, to me, those are 3 of the big ones that it was put up there for. So let's take a little look at the telescope. Let me see, I probably don't have this on. Okay. Doesn't want to switch. Okay. The pages should just, oh wait, maybe this. Okay. Okay. So the James Webb, as you can see on the left, looks very different than the Hubble. The Hubble still looks a little bit like how we picture a telescope. It's got a tube, and it's got the primary mirror, the secondary up top, and an instrument box. But the James Webb mirror is just out there, and it's got nothing to cover it up. It also operates in the infrared rather than mostly visible. The Hubble takes some images in infrared, but most of it was in the visible light spectrum. And because infrared is especially subject to light and heat, there's a sun shield on the back of that about the size of a tennis court, 22 meters by 12 meters, a gigantic sun shield. The planned mission for James Webb is about 5 to 10 years. But if it's built as well as we've built other things like the Hubble and the Voyagers, we can hope for many, many more years than that. Excellent. That's a good thing. The Webb's primary aperture is 25 square meters, which is almost 270 square feet. The mirror is broken into 18 segments with a focal length of 131.4 meters. The mirror is made of beryllium, and it's got a gold plating on it. And they covered that entire mirror with gold, and they only used 48.25 grams, which is less than 2 ounces of gold to cover that entire mirror. So that's about as thin as some of the gold jewelry I buy my wife. The Webb Telescope collects 6.25 more light than Hubble. So we're talking about a very significant increase. And here's another difference. The Hubble orbits the Earth at 355 miles. That was close enough to send a shuttle up to deploy it, and we even had a couple of trips to fix problems with the Hubble and to upgrade it. That's not going to be possible with the Webb, which sits at what's known as a Lagrange point, just under 1 million miles from Earth, or 4 times the distance to the moon. It had to be launched by a rocket, an Ariane 5, and had a long way to travel. And that's why it took us so many months to get our first images, because it was quite a step up in logistics. So simply put, a Lagrange point is a spot in space where gravitational forces of a two-body system and the orbital motion of a body balance each other out and form a nice little parking space. It's kind of like the eddy on a stream where you get a little spot where nothing moves. So the Webb doesn't sit at that point, it actually orbits that point. It goes around that point a little bit. There's 5 Lagrange points along the two-body system. And the one the Webb is orbiting is known as L2. So it's far away from all the space junk that we've put up circling our Earth. That's the good thing. But the fact that it's an eddy can bring a couple of meteorites and stuff in. There was already a tiny little impact on the mirror within a month after it was deployed, but luckily nothing happened. And by the way, L1 is where we parked our solar and heliotropic observatory, known as SOHO. That gives us when there's a coronal mass ejection, that instrument at L1 gives us about a 20-minute warning as far as how strong that ejection is. We have more of a warning that it's coming, but that's the first point we actually get to measure how strong it is. Just to take a quick view of the electromagnetic spectrum. Our eyes only see this much of the electromagnetic spectrum, called visible light. And they actually act like a camera at a 1/30th of a second shutter speed. So it's not enough to gather the colors that we see in nebula. When you see all those colorful pictures, if you look through a telescope, you would just see, in most cases, just the Milky Way. If you have a really big scope, sometimes you see some color in 1 or 2 of them. You can see some color in Jupiter, but for the most part, our eyes aren't strong enough to see the colors in the objects. And as you can see, there's a whole bunch of more electromagnetic spectrum. And we've got it pretty well covered. Hubble was mostly a visible light, but it did take some images in ultraviolet and came into the near infrared. James Webb is all infrared, near and mid infrared. And we've got the Spitzer, even takes it a little further. But we have even more covered, from the Swift and gamma rays to the Hubble to the James Webb to the very large array down in New Mexico, measuring radio waves out there. We've got it pretty well covered. And what you see sometimes when an image is produced, you'll see more than one telescope being given credit. And what scientists do sometimes is they take the information from different wavelengths and they composite it to give us more information in one picture. So it's a tradition now to release a special image to commemorate each anniversary of the Webb Space Telescope. And so we've just had our 3rd anniversary. This is not the image. This is a ground-based image of the same object, the Cat's Paw Nebula. This was taken by Macone Germiniani, amateur astrophotographer. Very nice. That was taken in visible light. And you see the red indicates a lot of hydrogen alpha. But this gives you an idea of the entirety of the nebula, which is 90 light years across. That means it takes light 90 years to go from one end of this object to the other end of the object. Kind of big. This also gives you an idea what the nebula looks like in visible light and just how much dust there is blocking the view of a lot of those stars that are there. So the Webb astronomers pointed the space telescope at just one of those little toe beans up top and discovered a subset of mini toe beans. And that's their picture of their anniversary picture. This is the Cat's Paw Nebula, more detail, taken in near infrared with the Webb. Now, the Cat's Paw is located about 4,000 light years away from us. So the telescope also acts as a time machine, because when something's 4,000 light years away from us, we're looking at how the Cat's Paw Nebula looked 4,000 years ago. To see how it looks today, we have to wait 4,000 years till that light comes to us. So the deeper we look into the universe, the deeper we look into time. That's why studying galaxies that are so far away from us gives us information about galaxy formation, because they're younger and younger. If we look 11 billion light years away, we're looking at a galaxy as how it looked 11 billion years ago. We're looking back in time. And that's why, one of the reasons why the Webb is so important, and its quest to look deeper and deeper into space will give us more and more information on galactic formation. This is in the constellation Scorpius, which is visible in the northern hemisphere. It's also inside of our galaxy. If you look on your computer, if you look this up on your computer, you will see amazing detail that you just can't see in something like this. This big toe beam, this is called the Opera House. You can see it's got a little Sydney Opera House thing going on there. And the source of that blue glow in there is most likely a very active hidden star near the bottom of that structure that's still hidden behind dust. Now, infrared has cut through a lot of that dust from the previous picture, right? There's still some dust here. Like this area right here is dark not because there's no stars there, but the dust is just so thick we can't get through it to see what's going on there. When you look to the lower left, we see stars are better resolved in the picture, presumably because they've been there a bit longer and they've burned away a lot of the surrounding gases and dust by their solar winds in a process called photoevaporation. They're hot stars that will have relatively short lifespans. Most likely, they measure those lives in millions of years rather than billions of years. The hotter and larger a star is, the quicker it's going to burn itself out. And so the big blue ones are going to be the first to go. Their lifespans can be measured in terms of tens of millions of years, where our sun, the lifespan is 10 billion years. So I suggest you look at that. I mean, even if you enlarge this area, you can see the star formation here, and you can even see the bow of a shock wave there's so many really interesting areas in this picture to look through. I highly recommend looking on your computer to take a look at that. Now, before we go on the more recent pictures, I'm going to show you a classic picture. This is the cosmic cliffs of Eta Carinae. I'm sorry, the Carinae Nebula. Eta Carinae is a famous star within it. On the top, you'll see the Hubble shot taken in visible light. And on the bottom, you see the infrared. This is the infrared taken by the Webb. So not only do you see how much dust it cuts through, but you also see the increased resolution of that big mirror. And one thing I'll point out, when these telescopes send back data, they're sending back data. In the visible light, it's very easy to map the image because each of the visible light from red to blue has a wavelength, and we can just take those wavelengths and translate them into an image. But when you're talking to infrared, if we took that data and translated it into an image, we couldn't see it because it's infrared. So what they have to do is they map the infrared data into the visible spectrum. So the longest wavelengths come out red, and the shortest wavelengths come out blue. But it's all false color. It's all in a wavelength that we can't see. And that's important to remember. Anything that's not visible light, some imager has made the decision of how to display that visually. Even visible light photos, you have scientists trying to display it. So hydrogen is red and oxygen is green. But amateur astrophotographers or astrophotographers that just want to make an image, they can play with the colors all they want, and it might not have any scientific meaning, but it'll be a really pretty picture. So just keep that in mind. Okay, so here's our first, and this is a recent discovery. This was, the Webb discovered a new moon orbiting Uranus. It was first seen on February 2nd of this year. It's designated S2025U1. And it's so faint that it had to be circled, even so you can pick up on it. It measures about 6 miles across, 90 football fields or so. You could walk it in under 2 hours. Or maybe some of you can, I don't know. and although Uranus is almost 15 times more massive than the Earth, and you think, well, yeah, I can't walk it in 2 hours because the gravity is just going to bring me down. Uranus is so less dense than the Earth that it's actually 0.89 times the gravity of Earth. So you would actually be lighter there, and it would be a little easier to walk. And as a bonus, the surface temperature of minus 320 degrees Fahrenheit would probably encourage you to walk a little more briskly than you usually walk. Matthew Tescareno, a member of the research team and a senior research scientist of SETI, notes that no other planet has as many small inner moons as Uranus. He also said that the complex relationship between these inner moons and the fate ring system hints at a chaotic past for the planet. And that makes sense, seeing that Uranus's axis of rotation is almost 98 degrees. And it's long been hypothesized that something hit that planet and sent it on its side. And so we're seeing more and more data of the rings and all the small little planets all point to a possible catastrophic event with Uranus. And great science just coming out of the Webb. Now there's a near-Earth asteroid 2024 YR4, and that was discovered in December 2024. And it caught the attention of the whole worldwide planetary defense community. And by the way, planetary defense was a tag that came up in the 90s when comet Schumacher-Levy hit Jupiter and did some visible damage to it with the power of more than all the nuclear devices on this planet. The tag planetary defense community came up. And that's the system of looking for asteroids that might hit the Earth or come close to the Earth, and also now how we might be able to change the trajectory of one of those. So when this first was spotted, Uh, They estimated it at about the size of a 10-story building, which has been confirmed. Originally, the asteroid was given a 1 in 33 chance of hitting the Earth within 8 years. It's got a 4-year orbit. But additional tracking spared Earth. There's not a chance that it's going to hit, but it's going to come close. And there's still a chance that it will hit the moon on December 22nd, 2032. In February, the odds were at 1.7%. It's been increased to 3.8% based on the Webb data observations and from ground-based telescopes. So that's about a 1 in 25 chance, and that's the latest. A 1 in 25 chance of it hitting the moon, and but that's still 96.2% chance that it's not going to hit the moon. Let's be a little optimistic here. And in the event that it did hit the moon, it would not be powerful enough to alter the moon's orbit, so they say. The worst event would be if it hit the dark side of the moon, so we couldn't look at it. But
On frame. Yeah. Body up there.
I don't know. Chinese probably beat us up there. But yeah, I don't know. That's, we're talking 7 years. That's not very long. So the Webb gave us better information and less uncertainty. But the bad news is that the size of the asteroid was on the high side of our original estimates, and the chance of the asteroid hitting the moon doubled when we had better information. This image is from May 12th of this year, 2025. Any guesses what we're looking at? Good guess? No? Yeah, that color definitely makes you think it's really hot. We're looking at aurora over Jupiter's North Pole. And we knew that, we've had pictures of aurora, but we're getting much better detail with the Hubble. On Earth, auroras are caused when energetic particles, mostly electrons, are accelerated by solar winds and geomagnetic storms. And then they excite the atmosphere, and then we see those beautiful displays. Mostly nitrogen and oxygen causes that. We also call that northern lights here on Earth. We've known Jupiter had aurora, and even images from the Webb have showed us that, even before the Webb. But the Webb has captured new details and details that are 100 times brighter than the ones we've experienced on Earth. So this is a much brighter aurora. And Jupiter has an additional source from auroras. First of all, it's got much stronger magnetic fields funneling these particles and the solar winds to its poles. But also, it grabs particles that are thrown into space by its closest moon, Io. And Io is the most volcanically active body in this solar system. And as a matter of fact, it shoots up so much sulfur. There's a toroid, which is a fancy name for donut. There's a toroid around Jupiter of this material. And so the magnetic particles grab that, force it towards the moon, and use those to excite the atmosphere to these super bright auroral displays. Another thing is that the Webb NIRCam, that's near infrared camera, is sensitive enough to show changes in small amounts of time, which we have not had the privilege of before. And scientists thought that changes would take place over like lapse of 15 minutes or more. But they saw what one astronomer described as fizzing and popping taking place sometimes by the second. So they're seeing a much more active aurora and changes that are happening second by second. These studies are giving scientists new insight about how Jupiter's atmosphere is heated and cooled. So there's some real information being gotten here, not just pretty pictures of aurora. In March of this year, Webb captured auroral activity on Neptune for the first time. Here we see on the left is a color-enhanced image of Neptune in visible light from Hubble. It's Wide Field Camera 3. On the right is the same image, but overlaid with James Webb near-infrared spectrograph data. And the cyan color that you see on the right, those splotches are auroral activity, and the white is clouds. So astronomers saw hints of auroral activity on Neptune when Voyager 2 went by back in 1989. But this confirms that they actually did see some auroral activity. And now we have confirmed auroral activity on Jupiter, Saturn, Uranus, and Neptune. All four of those we've seen confirmed auroral activity. So let's keep our focus on planets for a while, but go outside of our solar system. Does anyone know what a planet outside our solar system is called? Exoplanet. Yeah. Pardon me? Yeah. Here's a photo of the southern skies over near the south central pole. And I had the privilege of seeing that from New Zealand, March of this year. My son took me, generous son, took me to New Zealand, and I had a smart telescope as well with me. But what I want to show you here is Alpha Centauri, to the left of the very famous Southern Cross and the coal sack. Alpha Centauri, for you older folks, is where the Jupiter spaceship in Lost in Space was headed before it got waylaid and on many different adventures. Alpha Centauri is actually a 3-star system. Alpha Proxima, and then Centauri, Alpha Centauri A and B. It appears as one star to the naked eye, and it is bright. It's the third brightest star in the sky after Sirius and Canopus. That was it, Sirius and Canopus. And Venus, of course, is much brighter than that. But still, it's a negative 0.27. And the smaller the number in magnitude, the brighter the star is. And when you get into the negative numbers, you're talking about a pretty bright object. Mm-hmm. Mm-hmm. The closest star to our solar system is Proxima Centauri. It's about 4.25 light years. So that's the closest to us. And it's in the constellation Centaurus. It's a dim red dwarf. So it's a little easier to find exoplanets around Alpha Proxima. And we know 2 confirmed exoplanets are there, and there's one that's disputed and needs further confirmation. But that was pretty easy because it was dim. Now remember that the James Webb Space Telescope was designed to look at really far off dim objects. And so now to point it at something as bright as Alpha Centauri and try to find a exoplanet there, really, to me, it was one of the great feats that was accomplished by the team so far. A and B is a binary system separated by only 2.1 billion miles. So that's like us having another sun, a brighter sun even, right where Uranus is. So that's really pretty close. In another 25,000 years, they're going to alternate being the closest because that whole system is in motion. Right now, Alpha Proxima is the closest, but Alpha Centauri A and B are going to take turns being the closest to Earth every 80 years. But that'll happen in 25,000 years from now. So we probably won't get to see that. Proxima Centauri orbits the binary stars every 550,000 years. So confirming every exoplanet, as I said, around A or B has been very difficult due to their brightness. But Webb's mid-infrared instrument has given us the strongest evidence so far that there is indeed a giant gas planet orbiting Alpha Centauri. And if confirmed, it'll be the closest planet to Earth orbiting a star in the habitable zone. They call it the Goldilocks zone. It's in the zone where it's not too hot and not too cold. It's warm enough for water. Now, of course, since it's a gas giant, it's kind of a moot point that it's in the habitable zone. because life as we know it is not going to be able to survive on a gas giant like that. It couldn't support life as we know it. So the Webb, as I said, the Webb telescope was optimized for finding the most distant galaxies. And so what they had to do was they had to come up with a custom observing sequence just to look for the planets. And these images kind of point at the sequence of events. On the left is a ground-based digital sky survey. It shows the system as one light source. The middle is Hubble. So as astronomers say, Hubble was able to split the binary or resolve the star system into two separate stars. And so you can see A and B there. And then finally, on the right is an image taken by a special coronagraphic mask used to block the star. And what that's kind of, think of it as creating an artificial eclipse. It's blocking the light from the star so you can see better. If you ever seen pictures of a solar eclipse, once that sun is blocked, you see stuff around the sun that's just amazing that you couldn't possibly see in the glare of that light. So they've created that mask, and then we could see the candidate planet right here, S1. They've circled it. This was accomplished in 2024. And this is another series to show that putting the coronagraph here didn't just result in this picture. There was a lot of glare. On the left, you see the original Webb photograph, and you see the double set of diffraction lines. So that's caused by the two different stars. And then in the middle, we have a photo with the coronagraph in place. But the problem is that the telescope's optics and the mirror support produced stray light that interfered with the photograph, and they still couldn't see the planet. And so astronomers had to figure out what stray light the structures were creating, and then they wrote a program to remove that light interference that they knew about. So that's like a massive effort in programming and calculation. And when they did, they were able to reveal this exoplanet. And they got that done in August of 2024. Then, of course, once you discover an exoplanet, you need to confirm it by observing it again. So they went back in February of this year, and they couldn't find the planet. So again, the astrophysicists ran a bunch of simulations, assuming that the planet's orbit was stable enough not to be flung out of the system, and determined that in half the simulations of the orbit, the planet would be too close to the star to be detected in both February and April. So half of their simulations told them that they wouldn't be able to find it. So they still need to go back and confirm. And I have not heard that they've done that yet. But very interesting. It's just an amazing amount of math and science brought to bear on this project. Now, this is an artist's concept of what the gas giant, which is estimated to be about the mass of Saturn, might look like. And in this illustration, Alpha Centauri A is on the left, B is on the right, and the sun is right in the middle, kind of, a little over to the left. Again, it's an artist's concept. And by the way, I got this data off of a news release in August, and it just showed up in Astronomy magazine December issue. The exact same. I opened the magazine and said, whoa, that's a slide I use. So they finally got around. You know, there's a lag when you're printing a magazine, there's a lag in getting the information out, which is why it's great to read those press releases that come out of the James Webb site. So a PhD student, Ankikat Sanghi of Caltech, who was a co-first author on 2 papers covering the research, had this to say. and I thought it was very succinct. If confirmed, the potential planet seen in the Webb image of Alpha Centauri A would mark a new milestone for exoplanet imaging efforts. Of all the directly imaged planets, this would be the closest to its star seen so far. It's also the most similar in temperature and age to the giant planets in our solar system and nearest to our home, Earth. Its very existence in a system of two closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. So this is a big deal in exoplanet research. Yeah. Little bonus material for any sci-fi nerds out there. This book by Chinese author Cixin Liu, The Three-Body Problem, is an amazing book. It talks about a civilization living and a star 4 light years away from us in a three-body system. And it's called three-body problem because it's very hard to calculate, almost impossible, to calculate the orbits of a three-body system like the Alpha Centauri. And great book. If you don't like reading, Netflix came out with a series on it too, but I can't recommend it because I haven't seen it because I haven't finished the 3rd volume of this book. It's like 1,800 pages. So, but it's really good reading. It's hard. There you go. But this has the hard science in it. I don't think Netflix is going to have the hard science, and this guy does a great job with that. Pardon me? There you go. So here's one of the fronts that our knowledge of galactic evolution is growing. This is an image, and this isn't a Webb image. This is an image that we've had from Hubble. It's galaxy ESO 137001. It's a great example of a jellyfish galaxy. And jellyfish galaxies are a class of galaxies that seem to drip tentacles behind them, right? So star-forming material is kind of like dripping off the galaxy as it moves through space. This galaxy is part of this famous giant cluster, Abell 3627, the clusters of galaxies. And when you have a galactic cluster, a cluster of galaxies, it's not empty between the galaxies. There's material in there. A lot of it is hot gas in the areas between them. And so it's currently thought that this material asserts a drag as the galaxy moves through the cluster. And this drag strips some of the galaxy's material away, which then trails behind it. It's sort of like a headwind blowing the material away. As NASA notes on their website, the mechanism, which they call ram pressure stripping, hastens the loss of star-forming gas, which prematurely slows star formation and production in these galaxies. And we've seen evidence elsewhere that galaxies and clusters stop forming new stars earlier than galaxies that are not in a cluster. But the mechanisms involved are still not well understood. And hopefully, jellyfish galaxies will give us a hint. So this is the Webb image. It was taken this year, and it's believed to be a newly discovered jellyfish galaxy. It was discovered by chance by astronomer Ian Roberts at Waterloo University as he was sifting through James Webb images. You know, a lot of times that's how discoveries are made with these space telescopes. You get an astronomer who just wants to look through the images and looks for anything that pops out at him. And that's how this was discovered. He saw this and he realized, or thought he realized, what he was looking at. And this may be the most distant jellyfish galaxy discovered so far, with an estimated distance of 12 light years. The circles show the suspected, yeah. I'm 12 million light years. Thank you. Yeah, that was a typo. 12 million light years. It's distant. The suspected blue tentacles show are circled. And the ram stripping mechanism that produces the effect it's not believed to be rare because galactic clusters are not rare. However, this jellyfish stage of a galaxy is thought to have a relatively short lifespan, and therefore Roberts thinks that it may be unusual to actually capture images of these jellyfish galaxies. We don't really know. We've never done a systematic search for jellyfish galaxies. They've been discovered by accident, by looking, and so no one's actually done a survey to try to find these. So Roberts' data has not yet been peer-reviewed, so stay tuned. Right? Once an astronomer comes up with a hypothesis, he needs his peers to review that and to test his hypotheses, and that's at what stage this is. This data from the James Webb is really shaking up theories on galaxy formation. You know, in general, it was thought that the early galaxies were simply hydrogen and helium, and they had simple structures. And it would take a billion or 2 years for complexity to start to develop. That's been the theory for years. And also, that black holes would come on the scene later, because when a star the size of our sun, up to 8 masses, dies, what happens, it turns into a red giant, it throws off a gas shell and leaves a white dwarf behind. When you go to a larger star, there's no cataclysmic explosion involved. When you go to a larger star, say 8 to 60 solar masses, you get a supernova at the end. When the star keeps burning through the elements till it gets to iron, which requires more energy than it gives, and then you get that super cataclysmic explosion of a supernova. That leaves behind a neutron star. When you go above 60 to 80 solar masses, what's left behind is a black hole. And so it was thought that you have to have more complex elements. You needed a bunch of supernova events to throw those heavier elements out there. And to have black holes, you needed supernova events, a bunch of supernova events, to form those black holes. So the black holes would come on the scene later in stellar evolution. And what this data and other data from the James Webb is really having scientists scratch their head, because they're seeing the heavier elements earlier than they ever thought. They're seeing structure in galaxies more complex than they thought, going back within hundreds of millions of years of the Big Bang. And so there's a lot of rethinking on stellar and galactic evolution, which is exactly what James Webb was meant to do, is to help us understand this galactic evolution. So this image may either help with the confusion or add to the confusion. It's known as the Infinity Galaxy. You can see there's like a figure 8 there. NASA's website states that the object is a result of 2 colliding spiral galaxies composed of 2 rings of stars, seen as ovals at the upper right and the lower left, and 2 nuclei, black holes, of the spiral galaxies are seen represented in yellow. So you can see the 2 nuclei there, very nice bright yellow. And glowing hydrogen has been stripped off its electrons between the 2 galaxies, and that appears green. So astronomers have detected a 1 million solar mass black hole that seems to be embedded within this large swath of ionized gas. So not at the galactic core, but in here. 1 million solar mass. We're not talking about a small black hole either. You know, that's a good one. I didn't write that down. How far we're looking. Oop. I'm not sure how far this galaxy is. Sorry about that. So looking at this 1 million solar mass black hole, they think it might have been created through a process known as direct collapse, which is amazing. So that means that it's not a result of a supernova, But a star, the way a star is born, is it's a huge glass cloud that collapses upon itself until it gets hot enough to ignite, and then the outward radiation and the gravity finally balances out into what's known as hydrostatic equilibrium, and the star stays there forever. So what they're saying is that they think that black hole may have been born not of a supernova, but just a huge, huge cloud collapsing on itself to form a black hole directly, which is just right. It went right. It was so the cloud was so massive it went right into a black hole. And that's what's happening. Each of these galaxies have a black hole, and they're colliding, but there's a black hole here, and it's humongous, and it's not in the core of a galaxy, and it's huge, 1 million solar masses, and so the theory, right? Scientists come up with a theory, and now they've got to do a lot more observing, but the theory is that this might have been a direct collapse black hole, which just totally is mind-blowing. This is from NASA's James Webb Space Telescope, the NIRCam. There, there you go. We could rename it. The black hole dude. Yeah. Yeah. So I mentioned combining observations from different telescopes. Well, this is the Very Large Array radio telescope that's on Earth. And the center pinpoint of the radio emissions lines up perfectly with the center of the glowing gas detected between the two galactic nuclei. The map shows us the intensity of the energy that's pulling in surrounding material. So there's two observations that complement each other and actually strengthen the theory that the scientists have about what's going on there.
Got 8.3 billion light.
Thank you. I better write that in my talk, because I always try to get the, so that's 2/3 of the way to the Big Bang, right? Which is about 13.8 billion years away. Yes? Black holes, what this is showing is that the black hole is sucking up more and more. You know, we can never directly observe a black hole, but what we can observe is the accretion disk. When a black hole comes in contact with other matter, the matter goes around, heats up, and then disappears inside the black hole. And a lot of energy is created there as the black hole is gobbling up matter. And that's what this is pointing towards. This is showing that we can see, even in radio waves, that there's a whole lot of energy going on there. So we've been able to image the accretion disk on a couple of black holes. Because light never leaves the black hole, you can't image a black hole, but you can image the silhouette of a black hole in the middle of an accretion disk. But this has so much material around it, we can't even do that. It's hidden behind so much gas. And you know, the fact that it's thick gas and a lot of gas, maybe that supports the idea that the black hole was formed out of a very, very huge amount of gas and dust. Exciting stuff. But that's exactly what the James Webb was sent into space for, just this kind of data. Okay, I'm just going to go past this. Oh. Okay. The Webb is also giving us data on a number of theories that scientists have held for quite a while. We found unexpectedly massive galaxies, as I mentioned, in the early universe, where we thought we would see less complex ones. There's something known as the Hubble tension, where the data from the Webb suggests that the universe is expanding faster than previously thought. And this little gem from the JWST survey adds to our knowledge. Astronomers have a lot of catalogs of objects, like the Messier catalog, NGC catalog. This is called the JWST catalog. And JWST is the name of a catalog of objects that is short for James Webb Space Telescope Advanced Deep Extragalactic Survey. Extragalactic means that it happens outside of our galaxy. So it's a catalog of objects outside of our galaxy. And it's part of our effort to study galactic evolution. And this is done by imaging distant galaxies and studying their spectrums and their redshifts. The faster a galaxy is moving away from us, the more the spectrum of the elements in those stars are shifted to the red. They call that redshift. So the larger the redshift, the faster it's moving away from us, and the farther it is from us. And this survey has identified hundreds of galaxies that exist in what's known as the good S field that existed when the universe was less than 600 million years ago. So this is one of them. This is GS-Z13-1. This galaxy was observed to exist just 330 million years after the Big Bang, which is amazing, 13.5 billion years ago. This image is from the NIRCam, and the challenge to researchers is to explain how the light from this object, and what we're talking about is this object. These have different, these are much closer. You can see the redshift here is only 0.7. Z equals 13 is off the charts. So the challenge is, how did the light from this object pierce through the fog of neutral hydrogen that our current theories say fill the space at that time? The age of this galaxy is estimated by its brightness and redshift. And this is an area where James Webb excels, searching for the dim objects whose light is shifted so far into the red that it's moved entirely into the infrared. It's no longer in the visible light spectrum. It's so shifted, it's entirely infrared. This is just a close-up panel of the same thing. Initially, the redshift was estimated at 12.9, but subsequent evaluation of the spectrum confirmed a redshift of 13.0. That in itself is mind-boggling. How can you distinguish between 12.9 and 13 in a redshift? It's just amazing the precision of the instrumentation that we now have up there, making these observations for us.
Timeline was reionization.
Mm-hmm. Right. They posited a thick cloud of material that should not allow for light like that to escape, and yet there it is. Oh. So before the Webb started imaging, we only had one confirmed galactic candidate from the first 500 million years of the universe. Just one. It was GN-Z11. And although it is a very distant galaxy, it's not even in the top 10 list anymore. That's how much the Webb has added to our data. What we thought was one of the most distant galaxies is now not even top 10. It turns out that these ultra-distant galaxies are about 100 times more abundant than we thought when James Webb began operation. So there's another surprise to scientists, 100 times more abundant. Now, the current record holder announced May 16, and I think it's still the current. I haven't looked in the last month or two, but May 16th of 2025, it's still holding its spot, is MOM-Z14 with a redshift of 14.44. That puts this galaxy within 280 million years of the Big Bang. And this bright early galaxy does not fit our traditional theories of galactic formation at all. We don't know what to do with it. And by the way, the MOM survey stands for Miracle of Miracles. And it was initiated to determine whether some of these bright early galaxies really lie so far away. And after re-imaging and analyzing the galaxy's light, the research team pronounced MOM Z14 is a miracle and not a mirage. My favorite catalog is the WIT catalog, and that stands for what is this? And it does, I'm not joking, it exists. It's some interesting objects in there that scientists just, what is this? Throw it in that catalog. The brightness of this object can't be explained with a feeding central black hole, but rather it's explained by a bunch of young, bright stars. The galaxy is also very compact, about the size of the small Magellanic Cloud that we can see from the southern hemisphere. Okay, one last mystery I'll leave you with, and this is an important issue. It may not affect our lives directly, how the universe is going to end, but it's a fun thing that that people think about. If our universe lost the battle lost the battle of collective gravity on it, and everything finally would end up in a big crunch, like everything would reverse expansion and end up in a big crunch. That's the least likely theory, but it used to be scientists' favorite theory of maybe 50, 60 years ago. But given what we know now, the big crunch is the least likely outcome for our universe. The universe is expanding at an increasing rate. Think of putting marks on a balloon and blowing up the balloon. Everything is moving away from each other. Now, there's a couple local galaxies that are moving towards us, right? The Andromeda galaxy is moving towards us, and some scientists think it may collide with us in about 4.5 billion years. But aside from a couple local galaxies, everything is moving away from each other. The other extreme of the theories is the big rip. If dark energy continues to push the expansion rate of our universe to near infinity, we'll end up in a big rip where everything, including atoms, get torn apart because of the increase in acceleration. So that's the other end. The most likely scenario, at least currently, is the big freeze. By studying type 1a supernova in the late 1990s, scientists realized that the expansion of the universe was speeding up. That's where that idea started. And the supernova were dimmer than expected because they were further away than expected. They were moving away from us at a faster rate than we originally thought. So this expectation-defying discovery of dark matter, as Astronomy magazine puts it, showed us that it was very unlikely that the universe will end up in a big crunch. Rather, the gravitational tug of all the matter in the universe will not be able to overcome the inflating effect of dark energy. Currently, scientists believe that normal visible matter only comprises about 5% of our universe. Dark matter, 26%. Dark energy, a whopping 69%. So in about a googol years is one with 100 zeros after it, the last supermassive black holes will have evaporated and the universe will enter its dark era where no matter exists anymore. That's the most likely theory so far. The big freeze, that's right. Like the second law of thermodynamics, we go out with a, right? So the Big Bang we started with, and we go out with a little whimper. So on that uplifting note, so that's one of the big questions that scientists want to answer, and they hope that the data from the James Webb Telescope will help them with that. The ones that I just showed you? Oh my. Well, there's the Methuselah star, and Methuselah was a character in the Bible, the oldest character in the Bible. There's a Methuselah star that they measure its age as older than the universe. So that's kind of strange. There's a Hogue object, which is a wheel around another galaxy, and it looks like they were formed at the same time, that they weren't part of a collision, but they formed that way, and nobody understands how that could possibly be. because it looks like it looks like other galaxies where two meshed together, but they are sure that it was one object. And it's like a center object and then a big ring around it and a lot of space in between. That's a very strange object.
We have a question from one of our participants online. He asks, does Apophis have a greater chance of hitting Earth in the years beyond 2032? If they've worked the orbit out.
I believe it leaves our neighborhood after that. After the 8 or 12 years, that it actually leaves our neighborhood. It's like we have another moon for a while. And you know, the fun thing, I was talking to Nina, the fun thing about question and answer period on something like this is that each one of these topics that I've talked to you about, scientists have devoted their entire lives to studying that one little niche. And then I arrogantly stand up here and say, any questions about all this stuff? You know, really think about it. People spend their whole life studying just one aspect of this. And as you could see with the discovery of that gas giant around, recently, the amount of intelligence and cleverness is just amazing to me. To actually be able to model the stray light from your telescope and then come up with a program to subtract that stray light so you could see Alpha Centauri A's exoplanet, that's mind-boggling. That's why you younger guys, you got to take math and take science. You got to be really good at it. You'll be worth your weight in gold.
An astronomer named ARP.
ARP, yeah.
A-R-P.
He's got a catalog.
Think, your galaxy and a quasar, which is much further away.
Mm-hmm.
Did this Webb Telescope look at that connection to see if it was a real connection between the nearby galaxy and a very distant quasar?
They've seen galactic lensing, right? So they'll see a galaxy that's about 5 billion years away, and it's so massive, it has such a massive black hole that it's bending the fabric of space-time around it. And so they've taken pictures of quasars that were 10 or 12 billion light years away, and the light has been bent, and so that they see multiple images of the same quasar being bent around a supermassive black hole galaxy.
There's a link, a nexus between the local galaxy and the distant quasar, an actual physical link. Do you know anything about?
I don't. That almost sounds like quantum physics to me. It sounds like quantum entanglement. Yeah, yeah, but I don't. That's way beyond my pay grade.
But the look at the redshift report with that image you showed, looked like there were like 6 or 8 pixels.
I know. Yeah, exactly.
They got all the spectral information. Maybe they did 20 different, got the average of all, but that's not a lot of pixels.
You're right. To get a spectrograph to give you enough information to measure the redshift, I know, it's amazing.
There's another online question. Any updates on James Webb's observations of 3I Atlas? Has it been looking at the 3I Atlas?
You know, that's been off my radar. I haven't read anything in the astronomy feeds.
I haven't either.
Oh. That's a tough object too, because it's moving and it's moving fast, and the Webb was not designed to track like that. You're welcome.
Activities and Stephen.
Autograph, please. Sure.
Next
Here?
meeting, December
Yeah,
13th,
this one.
will be our holiday party for public event.
There you go. Sure. Right here?
Yes, please, but I don't have. I have to tell you, you're really popular, you know that?
I didn't know that. But thank you.
Well, thank you very much. It's a great.
Oh, my pleasure.
You mentioned the smart telescope you have.
Mhm.
What kind is it, if I might ask?
Oh, you're welcome.
'Cause I
Thanks for
think I'm
coming.
Looking at different kinds, some of them are pretty.
I did, you know, if
reasonable.
you go on the UACNJ site,
Huh?
I did a talk on it that you
Yeah.
might find interesting. What I had the